get started. So I'm very happy to announce our next speaker, Patricia Klein from Texas A&M University. She'll be giving the second talk for the Gröbner Geometry and Applications session.
Thank you for the kind introduction, and thank you, of course, for the excellent setup yesterday. And what I want to talk about today is mostly how we should think about Gröbner degenerations, what is the geometry we're trying to record, and what is the mechanism that records it. If there's time, I'm going to do one sort of larger example in a standard case, but if I'm being entirely honest, I don't think there will be time. And in that case, I'll do that instead on Friday. So what I want to talk about first are the key invariants of a variety that we might be interested in describing. We've seen many times before that a variety is described by the vanishing of certain polynomial equations. I'm mostly going to be thinking in a projective setting, which means that all of my ideals are homogeneous. This was also Adam's assumption. It's a natural place to work in for intersection theory types of questions in particular. So when you first are walking down the street and you meet a variety, you have a get to know you conversation, and you want to know, what's its dimension? Just how big is it? And dimension we can see is the Kroll dimension of an associated ring. It's also just, let's work over C. We're friends today. Also, characteristic P is wonderful. Let's work over C. So then we just want the complex manifold dimension anywhere we might see it. So, and if there are components, take the biggest one. So, for example, what we have projected here, the dimension is 2 because, I've got a manifold structure here. It looks kind of planey. So dimension 2, that's how we should think about dimensions of our varieties. The next thing we might want to be interested in is what's the degree of a variety. So how much does it bend around? This generalizes the notion of degree of a polynomial equation. So here's not the way that you learned about degree as a child, but here I'm just going to be in R2, and here's some function. We know maybe odd, even, so we know this is odd degree. But the way that I want to count degree here is just by passing a line through it and counting points of intersection. So 1, 2, 3. So I chose my line so that I'm not hitting any of these, exciting points where we might bounce. And, this is really over C. So here, imagine I would also get 3 points. We just couldn't see them in this drawing. But the degree in any way that we've come to think about degree, of a function like this, is the number of points of intersection that I get when I pass a line through it. That's a notion we can generalize. So the degree of a projective variety is just the number of points of intersection that I get when I intersect with a linear subspace of complementary codimension. So if I'm in R3, if I'm in 3 space, and I have something 2-dimensional, I want to pass a line through it. If I'm in 7 space and I have something 4-dimensional, I want to slice with a 3-dimensional linear space. And I do this in a generic way. Typically, you get the same answer. The answer that you get typically is the answer that we want. This only detects points of intersection if you're reducible. This will only detect points of intersection for the largest components. So, for example, if I have a line with a plane through it in 3 space, well, this is dimension 2 because the dimension of a plane is 2. That's the largest thing I see. So I'm going to compute the degree by passing a line through it. But my line can be wiggled away from this other line. 2 lines in 3 space you expect not to intersect. So degree can't tell the difference between plane with a line through it and just plane. So when we're thinking about degree, we want to really just be thinking about the top dimensional components, and we're counting points of intersection. And this is recording the information, how bendy am I as a variety? Are there questions about what dimension and degree mean. Yes.
Sorry, what was the specification on the linear space that we're intersecting on the guy with?
It's a complementary codimension. So a curve is dimension 1. I'm embedded in 2 space. So 2 minus 1 is 1. And then, well, the answer that we get should be invariant under wiggling. So we want to say it doesn't count if I'm tangent somewhere. That's not a stable answer. Dimension and degree are also things that are encoded by the Hilbert function. So maybe some of us have seen some of these facts before. Well, we've all seen some of these facts before. Maybe some of us have seen all of them, and some of us are calling the information for the first time. But the Hilbert function, the Hilbert polynomial, record the information of dimension and degree. And Fred told us that the Hilbert function is preserved under Gröbner degeneration. So that means that if I start with an ideal and I move to the initial ideal, I've preserved the information of dimension and degree. So that's something that I can hope to read off from the initial ideal if I understand the initial ideal sufficiently well. Let's take a look at what happens when we Gröbner degenerate to see how we can take something that's maybe complicated and geometrically find ourselves in a situation with something easier. So here's a variety that's cut out by xy minus z squared. These s and these t, these are artificial. These are scaling things. I'm going to be taking a limit. We can define Gröbner degeneration in terms of a limit, and geometrically, that's often a very useful way to think about it. So that's a formal introduction to that is in Eisenbud and sort of the reference for the course. And what I want us to do today is just sort of do the heuristic intuitive thing and make some numbers bigger or smaller and look and see what happens to our variety. So xy minus z squared, the real variety that we're cutting out, s and t, formal things that we're taking a limit on. So the first thing I want to do is t right now is 1, and I'm just going to slide t down to 0. So when I slide t down to 0, I'm getting rid of the second term here, this tz squared term. So let's all watch together. Ooh, ooh, ah. And it's coming right together there. And now we have a union of coordinate subspaces. This is great because a fact is that if I have a union of coordinate subspaces, all of the same dimension, the degree is just the number of coordinate subspaces I have. A coordinate subspace means an axis or the xy plane or the xz plane, something that is named by the coordinate axes and so on in higher dimension. So here, the degree is 2 because I have 2 components and they're both top dimensional. So once I get down to union of coordinate subspaces, let's assume we're equidimensional, I just count the components and I've found the degree of the initial ideal. I therefore infer the degree of the variety I'm studying. So does this seem good to everyone? It's really hard for you to say no. So this is our favorite example. And let's think about geometrically what's happening here as we perform this limit. So we're just making, right now, we have some family of equations to xy minus z squared. And here, as t gets smaller and smaller, this last term is becoming less and less important. And so for xy to be 0, if the z is not really contributing, then this function in the limit is 0 if and only if xy is 0, if and only if x is 0 or y is 0. And so one thing that we see in that is that z can be whatever it wants. We've gotten rid of the z. This is really the picture of a Grevlex degeneration or a Revlex degeneration. It doesn't matter that it's graded. So whenever we're doing this, we're getting this cone over z. Because z is allowed to be whatever it wants. We got rid of it from the equation. Okay, now we're going to put this again back to be 1. Also a Revlex degeneration. Let's think about this as being Revlex on x. So here we have now the xy term getting very small, not contributing. So in order to have an answer of 0, we need the t, which is just 1. So we need the z squared term to be 0. Here, eventually we get this plane, but we need to remember that we're getting the plane twice. So this kind of degeneration is a little bit harder because it is not properly described as a union of coordinate subspaces. Set theoretically it is, meaning this function vanishes exactly when z vanishes, but there's extra remembering that we have to do, and that's the multiplicity. So here we're getting the xy plane, but we're getting it twice. So we want to think about this as having taken this variety and just projected it onto the plane. You're missing half the points, and that's because this graphs over R, not over C. But you want to be thinking about having all points in the plane at all times. So here the way to see that this is degree 2 is going to be, well, I pass a line through my plane, and we want to think about this as sort of getting the point on either side of the sheet as they're floating over each other infinitesimally. Or any other way that you like to think about, I'm getting this plane, but I'm getting it twice. Radical initial ideals are more closely related to the ideal that you're studying than these non-radical ones. The precise statement is due to Conca-Barbaro about 5 years ago. And that is that the extremal Betti numbers of a radical initial ideal are shared with the extremal Betti numbers of the homogeneous ideal that you started with. This generalizes a Revlex picture from Herzog, I think. But anyway, a radical initial ideal, for example, is Cohen-Macaulay if and only if the ideal you're studying is Cohen-Macaulay. Otherwise, you can start with something Cohen-Macaulay, degenerate, get this more confusing non-reduced picture, and maybe it's worse. Maybe the projective dimension changes, although the codimension doesn't. So we've seen a lot of definitions of Cohen-Macaulay. In the homogeneous case, another one is that projective dimension equals codimension. So this limiting process that we're doing here by moving a variety around, we can also do this limiting process within the free resolution. And so if you take a resolution of R mod the initial ideal, interpret it as this limit with this t in it, take a minimal one. If you then take the limit, you will still get a resolution of R mod I, but maybe it's not minimal. So that's telling you that R mod I can have a shorter minimal free resolution than R mod initial does. It can never be longer. So that's how we would formalize this picture to understand that we can start with something that's Cohen-Macaulay, degenerate, and get something that's not Cohen-Macaulay. So things can get worse in the limit, they can't get better. And that's something that you're doing algebraically as an exercise, showing that if ni is radical, then I is radical, for example. Okay, let's just look at a couple of other pictures. So here is something that is more in the geometric vertex decomposition setting. Actually, why don't we do a third one, the third one before the second one. Here, this is not homogeneous. You can think about this as a slice at a W. It's not a good picture over R if I make this homogeneous. So here, this is going to be another Gröbner degeneration. This is going to be a Lex degeneration for Z. And so what happens is we take that ball and we just flatten it into the XY plane as Z becomes the most important term of that equation. Because once Z is really, really big, then once that term is really, really big compared to the others, then we really only care about it. So mostly this is just to to show you what degeneration looks like. It's stuff that's similar, limit. We'll do one more, and this should look like geometric vertex decomposition. So here we have y is going to be our most important variable. So y is the thing that we're going to focus on. And we're going to focus on it by taking this slider that's attached to y and taking it from 1 to 500. So here, what we're doing is we slide like this. And now over here, we started with something degree 2, we end with something degree 2. This is a union of subspaces. It's not a monomial ideal yet. When we do this geometric vertex decomposition, we're going to get y times x minus z. So we could do another step and get yx if we wanted to. But we can, these Gröbner degenerations that are not all the way to monomial ideals still look the same. They just still look like sort of flattening out our variety. So here we're getting one of our components is the xz axis coming from the y, and the other component is x minus z is 0, and y is whatever it wants. So always, if we start with something irreducible, we will get one component that lives inside of the plane determined by y equals 0. And that's something that you're doing algebraically as an exercise. You're showing that if I is radical, then n is radical. That's the equivalent statement to if I start with something irreducible, I'm getting exactly one component when I slice by y equals 0. The other thing in this case is one component because, you can't graph large things basically. But that can actually have several components. So even when I is radical, this ideal C that Sergio defined for us yesterday, it need not be radical. It does still have to be equidimensional, but that's it. So it could have many, many components. I guess the last thing I wanted to say is one way that we can think about this is we take a solution to our equation here, just the usual one where u is equal to 1. And then we want to say, okay, if I'm propping up y to make it really, really large now, then that's the same as sliding myself over to, let's say, the y equals 1,000 slot, taking the slice of my variety there, and then just moving it over to the y equals 1 slot. So we want to think about this as taking the variety and really squishing it sort of along the axis. We're collecting its mass. And that's how it's coming to this flatter picture. Okay, questions about how to picture these or what we're preserving? Yes. This is a Desmos 3D. It is free on the interwebs, and I use it. I am not particularly visually inclined, so if I need to sort of envision how a variety is moving around under some limit, I 100% of the time graph it and look at it. Love Desmos 3D. Great question. Most important question of the day. In the limit surface area, we go down a dimension. So so certainly there maybe you mean not in the limit, but just as we're. I think it goes down, but I have never thought about this. No. That it can't be unchanged, right? It's got to go. That's a good question. I've never thought about surface area things, so maybe there is something that you can track through that, but I wouldn't know how. Okay, so now I want to make this go away. How do I do that? I guess the last thing, maybe I should have done this while we were waiting, is I want to talk a little bit more about how we should picture Cohen-Macaulay in this case. So we know that depth equals dimension. That's a definition we've seen a lot before. And that's something that's really good for homological algebra for inductive arguments. It's a very work with it kind of definition, although it's maybe not so intuitive, at least I find. We've also seen vanishing of local cohomology be gestured at as motivation to take a local cohomology course when available. This is also very important in the geometric vertex decomposition story. As far as a goal, why do we study Cohen-Macaulayness? Sarah told us a little bit about, well, she alluded to the upper bound conjecture, now upper bound theorem, where this was this is kind of how Stanley Reasoner stuff got started, where you want to count faces on a polytope and you want to maximize it. And this turned into a Hilbert function computation. And so Stanley generalized it using Stanley Reasoner theory, noticing that when you have a particularly good complex, then your Hilbert function is just going to be a scalar multiple of the Hilbert function of a polynomial ring. So Cohen-Macaulay in this homogeneous setting, we can think about as anything that's controlled as the Hilbert function is very well understood, because we know from stars and bars counting the Hilbert function of a polynomial ring. And so we can sort of scale that uniformly in a way where we don't get cancellation we're not expecting. So, and it turns into these really concrete combinatorial conclusions, like counting numbers of faces through these H-vector descriptions you may be seeing in combinatorics. In a geometric way, we're also interested in it from the standpoint of intersection theory. So suppose that I have two irreducible varieties, and they're of complementary codimension, so they're going to intersect in finitely many points. If both of my varieties are Cohen-Macaulay, then I can compute the number of points of intersection by just taking the length of one finite length module. So it's going to be polynomial ring mod the sum of the two ideals that define my respective varieties. If I'm not Cohen-Macaulay, then I have to do alternating sum of lengths of tors. So if everyone inside is Cohen-Macaulay, it's just tor 0. And we're happy with tor 0. This is R mod sum of ideals. And we can count vector space dimension there. You've been practicing this week. Otherwise, tor is hard. We saw that briefly, and we decided it was hard. And so Cohen-Macaulay in the setting of intersection theory is the right condition for being able to do our computations smoothly. So our goals are often to count stuff, at least if you do the kind of math that I do. And either that stuff is going to be stuff like faces of a polyhedral object, or it's going to be stuff as an intersection theory, number of points of intersection. And in both of these cases, for related though a priori different reasons, Cohen-Macaulayness is a goal. So one thing that we like about this geometric vertex decomposition story is that it is a way to establish Cohen-Macaulayness. It is also a way with some other stuff to establish primality and normality. And those are also probably things that you've thought about before and also view as desirable. So what I'm going to do in my remaining 3 minutes is state a couple of results and then gesture at some ingredients of proofs. And then on Friday, we'll do a big example carefully. So proposition, and I'm going to label this with a star because I'm going to want it again on Friday. If C and are homogeneous. I'm going to say F, I guess. F is homogeneous. Set J to be C plus N. If F is a regular element modulo N, so a non-zero divisor modulo N, equivalently this colon, nothing knocks F into N that wasn't already in there. R is the ambient ring. If R mod N is Cohen-Macaulay, and height N equals height C minus 1, sorry, yeah, N is smaller. Then height J is also equal to height C, and J is unmixed or Cohen-Macaulay if and only if C is unmixed, respectively, Cohen-Macaulay. So this looks like a lot of hypotheses in combinatorial settings, in the type of setting where we're doing geometric vertex decomposition. Most of these are often cheap. When Sergio told us about geometric vertex decomposition and when Sarah was telling us about vertex decomposition, one thing that we noticed that was maybe kind of hard to verify was unmixedness, because prime decomposition is hard. And so this is a core ingredient in inductive arguments, like the one we'll give on Friday. So what we want to do is we want to view N and C as being in the inductive case, and J is a thing we're trying to study. Our inductive argument will have told us that C and N are unmixed, typically also Cohen-Macaulay, and will tell us the heights. And then we will use this setup to conclude that J is also good. So this, oh, I'm sorry, was I supposed to go to 11:35? Yeah, great. So then by great, I mean sorry. So proof ingredients. Here's just a big one. Is going to be local cohomology. And a good reference for this type of thing is Nagel and Migliore notes from a Torino workshop. And these are on the archive. I think it's called, liaison related stuff. That's not the title. So keyword, basic double G-link. So this is where some liaison theory is appearing. But you don't have to know all of that to get stuff like this. The core ingredient is a setup like this informed by liaison theory, and then it's a local cohomology argument. And I'll end there. Sorry for going over.